In question 2, we've got a particle on a rough horizontal plane being pulled by a force of 28 newtons, and there will be friction, F newtons, opposing that motion. And we're asked to find the normal reaction force from the plane to the particle. And there's my version of what's going on. I've included the reaction force upwards from the plane on the particle, called it R, and I've also put on the weight of the particle, which is 5 times g, pointing downwards. And we're asked to find the value of R. So if I resolve vertically, the acceleration in that direction, A is 0. So the forces will balance. So simply R, which is the positive force, must equal 5g, the opposing force. And if we put in g as 9.8, this turns out to be 49 newtons. So in part B, we're now told that the acceleration, because of the force pulling the particle, is 1.4 meters per second squared. And we're asked to find the value of the friction that the particle experiences on the rough plane. Well, the equation that links forces and acceleration is F equals ma. And again, if I apply that in a positive direction going to the right, the forces to the right will be 28 minus F is equal to the mass of the particle, which is 5, multiplied by the acceleration, which is 1.4. And if you do the maths on that, it turns out that F is equal to 21 newtons. It's always good to check that your answer is roughly sensible. Yes, the acceleration is to the right, and the friction force is less than 28, so it proves that we've certainly got a force of the right magnitude. So part C, we're now told that the coefficient of friction between P and the plane is mu. Find the value of mu and give your answer to 2 significant figures. Well, as the particle is moving along the plane, we are in limited equilibrium. The friction has given up resisting up to the point that the particle is now able to move. So in this condition, we can actually say that F is equal to mu r. You see, as the pulling force increases up from 0, the friction increases because at that point it is less than mu r. We are not in limiting equilibrium because the particle is not going to move. But as soon as we're moving now, friction reaches its maximum. So at that point, F does equal mu r. So substituting our values in, we get that mu is equal to 21, the friction, divided by R, which is 49, and this turns out to be 0.43, and that is two significant figures. And those are the answers for question 2.